Look at the idea of cardinality, and that before we actually get into this, I want to make sure that you do understand what injective, surjective, and bijection function means. And if you don't understand, you can check one of my earlier videos I made on it that talks about it. But make sure that you understand that before we actually get into this, right? So let's get into this. Our first big question is that how do we compare the size of two sets? Like naturally, how would you compare if something is bigger than another? Let's say set A is 1, 2, 3. So there's 3 elements. Set B is 1, 2. How would you compare the size of these two? Well, that's obvious, right? Because in set A there's 1, 2, and 3. So there's 3 elements. In set B there's 1 and 2. So there's 2 elements. So naturally, we can conclude that set A has a bigger size than set B. So the natural method of comparing two sets is by counting, right? All we have to do is to count the number of elements in the A and B, then compare the two resulting numbers. And if the numbers are equal, the sets, they have the same size. So otherwise, one set is larger than another, right? But how mathematicians compare sets is not counting. Is that what they do is something called matching, right? So imagine in a club and there's a bunch of men dancing with women, and that if every man dances with exactly one woman, and that if we observe the crowd and see that no one is left out, we can immediately conclude that there's a same equal number of men and women in the club, right? Because every man dances with exactly one woman, so there's a match. So this is where the word matching comes from. There's a 1-to-1 match between each one of them, and that if we see that nobody's left out, then there must be an equal number of men and women in the club. So we conclude that the size of the set A, which is men, set B, which is women, are the same, right? We can conclude it that way by counting. So this method is interesting because something outside of mathematics topic, but in primitive cultures where counting methods were hardly developed, people are using matching all the time. So our ancestors use matching method all the time. Like a farmer may pair goats with a bunch of carrots to make sure that he has enough to feed the whole herd. It is also known that some children in their early childhood life that they use the matching method before they learn how to count. For instance, a 2-year-old or like a child might help his mother set up the table for dinner, and by picking by placing one spoon next to each plate, and then realize that he's short of spoons or has too many, right? This task doesn't require the ability to count, but has the same outcome of the way, right? It has the same outcome as the ultimate goal is to compare the size of two sets. And in the children's case, in this case, if they don't count the number of plate that they have on the table and they don't count the spoons that they have, what they can do is that they can just match, just place one spoon next to each plate, and at the end, if there's no plate left out and there is no spoon left out, then we can conclude that the set of spoon and the set of plate is ultimately the same, right? So that's how it works. This is the matching method. So now we get into the after that all that talk, we get into the actual definition of counting that we have here. The definition: two sets A and B are said to have the same cardinality if there is a bijunction between them. Notice that I've written the last part using red pen because that's all that matters at this point, is that if it is a bijection between them, right? And I assume that you already know what bijection is, so I'm not going to get too into that. But what does it mean that it says that two sets A and B are said to have the same cardinality? So what is cardinality in mathematics? Well, cardinality is a more accurate term used in mathematics for the number of elements in a set, right? It is more precise than size, because a lot of time when you say size, it's not rigorous. It's like more ambiguous because it might refer to the length of the area, or it might, like, we can say that areas has a bigger size. But when we say cardinality, we're talking about the exact precise term for the number of elements in a set. So it's less confusing if we use cardinality than size, because size is not rigorous, right? So, and that bijunction means that the sets A and set B can have like their injective and they're also subjective, which we call that they're bijective, right? So if there's a bijection between them, it means that they have the same cardinality. So enough of with all these definitions. Let's go into an example. So let's start with a really easy one, with set A being A, B, C, D, and set B being E, F, G, H. Well, again, the natural method is that we count number of elements in set A, which is A1, B2, C3, D4. So there's 4 elements in set A, and in set B there's E, F, G, H. There are 4 elements. So we conclude that they have the same cardinality. But how would we use the bijection way to do this? Well, we use it by defining a function that goes from A to B, like this, where of course A is equal to ABCD and B is equal to EFGH, and that we define, let's say, f of A is equal to E, and that f of B is equal to F of C is equal to G, and that f of D is equal to H. So we have somehow created a function right here. We can write it like this. Maybe I use the diagram I used in my last video would be more helpful if we have A, B, C, D, we have E, F, G, H, right? This is like this. We assign A to E, we assign B to F, we assign C to G, we assign D to H, right? So as you can see, this is clearly bijective, right? Because first is 1 to 1, is injective. So it satisfies the definition of an injective function. So it's injective. Also, it's surjective because there's no element in set B that is left out that has no corresponding element in set A. So we say this is surjective. So this is injective and surjective at the same time, which means that this is bijective. So there's a bijunction between set A and set B. So we can now conclude that they have the same cardinality. So you got to get used to this method of matching that we're doing here, of proving that it is an injective function and a surjective function. Because you can't, like on a math exam, you can't just say that, well, I count that in set A there's 4, and then count B in set there's 4 as well, so therefore they have the same cardinality. That simply wouldn't work. You got to get used to this more rigorous method of showing that they have the same cardinality. So that's where you need to get used to. Well, so let's take a look at the next example. Next example is that set A has 3 elements of X, Y, Z, and set B is actually I should probably put 2 bracket around this empty set. So set B has 1 element, which is the empty set. So there's 3 elements in set A, and there's 1 element in set B. So again, by counting in the intuitive way, there's definitely more element in set A than set B, right? But how we use this? How we show that there's no cardinality between these 2 sets because there's more element in set A than set B. So how will we show that? By using the formal definition of cardinality. Well, we show it by showing that there's no bijection between them, right? So again, we define a function that goes from A to B, and as you can see, since there's only 1 element in set B, right? So the only thing that we can ever do is to assign each element in set A to element in set B. So it's going to be like f of X is going to equal to empty set, f of Y is going to equal to empty set, f of Z is going to be equal to empty set. If we use the 2 circle method that we use, it's going to be X, Y, Z, all connected to empty set. And this is clearly not injective, right? Because the definition of an injective function says that a element in set B at most can have 1 corresponding element in set A. But in this case, we have X, Y, Z all connected to empty set. So therefore, this is not injective, even though it's surjective, but it's not injective. So therefore, there's no, it's not bijective. So therefore, there's no bijection between A and B. So we conclude that there doesn't have the same cardinality between these 2 sets, right? So you gotta get used to matching method. Like you gotta get used to this method instead of counting, right? So let's take a look at the next example that we have. A is a set that goes from 1 to 3 all the way to 100, and B is a set that B is just integers, all integers, right? So how will we? Well, intuitively, again, speaking from the counting method, they definitely should not have the same cardinality because there's like an infinite number of integer, but there's finite numbers of element in set A, right? So one set is infinite, one set is finite. So therefore, they must not have the same cardinality. So how will we go from the the definition method? Well, the definition method, let's just do it again. Assume f is a function that assigns a to b. So what will happen is that f of a, then the image of f of a, so the image is defined as f of a, right? So we plug in the domain into our function. Is at most, this is at most 100 element. Because each element in set A can only be assigned to one element in set B, right? So there's only 100 element in set A, so therefore there's only 100 as element that can be assigned in set B, right? But as you can see, this is at most 100 element, but there's infinite element in all the integers, right? So therefore we can say that there is more element in the, so therefore there's no like fa consists at most 100 element, as like the integer contains more than 100 numbers. F cannot be surjective because it's gonna be like if we use the circle thing again, it's gonna be like one blah 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 100 each one of them, and then here's just infinite number of them, right? You can at one time you can at most assign one element in set A to one element in set B, but there's only 100 of them, so you can only assign each one of them to 100 of random integer that you can choose, right? But there's more integer than 100 integer, so therefore we conclude that this is not surjective, as there will also be integer that will not have a corresponding element in set A. So therefore we conclude that this is not surjective, which means that this is not bijective, which then means that there's no bijection between set A and set B, which we can conclude that they do not have the same cardinality. And then let's look at our last example, which is the interesting one, because I say that this is interesting because this is kind of where the counterintuitive begins, right? So our set A is 1, 2, 3 goes to infinite, and our set A is just a natural number, and our set B is 2, 4, 6, which is all the even positive integers, right? So as you can see, some of them, like if you use your intuition, some might say that B is bigger than A, right? Because they think that if I have a line like this, and it goes from 1, 2, 3, 4, 5, 6, blah 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 blah, and I have two. This is even positive integer, 4, 6, blah 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 blah. They will somehow, like logically speaking, they think that this is 100% gonna have more element than our even positive integer. But that turns out not to be the case. That's why using the definition is important, because you cannot always rely on your intuition on whether or not it has the same cardinality, but you could always rely on the definition. So what does the definition say? Well, we do the same thing again. We assign an element. So ultimate question that we need to answer now is that can we form a bijection from A to B? Because if we can conclude that they have the same cardinality. So let's do that. So let's say that f of assign A to B, and the function will just be f of n is equal to 2n, right? Because let's say if n is 1, then it becomes f of n will just becomes 2, or if n is 2, f of n becomes 4, right? So there's like we're matching it, like 2n is ultimate the form of an even positive integer, right? So f of n is equal to 2n, it will be our function in this case. And as you can see, if we look at this function right here, we can just prove that this is injective, right? Because to prove that it is injective, what we need to do is that we need to assume that f of x, or f of n1, is equal to f of n2. And this will implies, if this is indeed injective, this will implies that n1 is equal to n2. And in this case, we have 2n and 2n. So let's write it. So 2n1 is equal to 2n2. And then this implies that if we divide both sides by 2, so 2, 2, which implies that n1 is equal to n2. So f of n1 equal to f of n2 indeed implies that n1 is equal to n2. So therefore it's injective, right? So how do we prove the surjective part? Well, if we write it, let's rewrite the function. Well, f of n is equal to 2n, right? Well, if we say that, let's just fix some y in f of n, right? So we can write this as y is equal to 2n. So now we solve for n. How do we do that? Well, we just divide it by 2, right? So y divided by 2 is equal to n. Therefore, we prove that it's surjective. Why? Why do we? How can we prove that this is surjective? Well, as you can see, every y, which is every element in our codomain B, right, divided by 2, it can, like, every one of them has a corresponding n by dividing the element you choose from set B by 2, right? So that's why it's surjective, because no matter what, because okay, actually I should write this as in B. This is more convenient, okay? And then as you can see that no matter what element you choose in B, right, you can always divide that element by 2 and you can always obtain a corresponding element in A. So we can say that we can conclude that every element in B has a corresponding element in A, which then leads us to the conclusion that it's surjective. So we just prove that this is injective, surjective, right? So therefore it's bijective. So we have successfully proved that indeed natural number and even positive integer has the same cardinality. So they have the same number of elements in their set, which is really, really counterintuitive, right? Because as you can see in this case, now using that 1, 2, 3, 4, 5, there's more gap between even positive integers. So therefore, even positive integer must be smaller, right? Or it has less cardinality than natural number. But it turned out to, by the definition of a cardinality, it is not the case that indeed they are eventually the same. So that's one little math fact that you can use to surprise your friend, maybe by asking them, like, is there more natural number or is there more even positive integer? And that at the end, the answer is ultimately they are the same. They have the same cardinality. Yeah. So that'll be my video on cardinality. In the next video, I'm gonna into the more complicated stuff, such as, is there more a natural number than rational number? That one will be a hard one to do, but I'm gonna do it. Yeah. So if you like the video and if you learned something, hope you can subscribe to my channel and keep on the follow up.